Hi, everyone. I'm Francesco Bongiovanni. I am the Supercomputing Application Service Group Leader at LuxProvide. So I manage a group who is responsible for the whole user support and software stack of MeluXina. So first of all, who of you have heard of MeluXina in the audience? Okay. So for those of you who did not, fair not, I will gonna show you what a supercomputer is, what is MeluXina. As I was involved actually from the very first day, I'm one of the main designers of the machine when I was at LIST, so the Luxembourg Institute of Science and Technology, where I was a researcher and I was managing the HPC over there. In fact, when I joined another team. I used to lead the team who was managing the machine on a day-to-day basis. And then after 2 years and a half, I created a new group, and that group basically user support and the software stack. So it's going to be a long journey. I have a lot of things to share, and we have almost 2 hours. I will go on MeluXina, not probably, I will go on MeluXina and show you around and show you nice things, okay? But so the journey starts in this wonderful land of computer science. So I love this picture because it represents basically the whole ecosystem of our field, with Mordor being up there, so theoretical computer science. So we're not going, I will touch a bit on this. So I hope that you're not afraid of Greek letters, because we're going to see a lot of them. So it's nice that supercomputing is actually almost at the center of this image. And we'll go around computational science, because when you do big data, I assume you do science with it or other things. We're going to touch, obviously, a lot actually, about architecture, hardware, because you have to understand your hardware when you work on a supercomputer. Then after, we'll go around and we'll wander around big data, machine learning, and AI, okay? So it's a packed agenda. So marketing pitch. So LuxProvide was set up by the Ministry of Economy to basically deploy and manage MeluXina. So soon, actually, MeluXina is going to have siblings in the name of MeluXina AI. So we are one of the first AI factory. And so the AI factory part already started in April. And with our partner, Lux Innovation is managing it. And the machine, we're working on it. We're in the middle of actually the procurement, so I cannot tell you more about it, just that we are in the middle of it. And then we're going to also, so last year we were very successful in terms of projects, because we also got to deploy a quantum machine. So Luxembourg is going to have MeluXina Q. So you see, we are reusing the name MeluXina because people know MeluXina but do not know LuxProvide. So MeluXina AI, MeluXina Q, and MeluXina. So and after probably other machines. So we were set up basically to give to the ecosystem access to those machines. But the Ministry of Economy did a smart move when it set up LuxProvide. They said basically, guys, we're going to set up for industry first, in the sense that if it's good enough for them in terms of high availability, security, and so on, then it's going to be good enough for research, because the research is going to love the fact that you have a highly available machine and secure and so on. So, okay, fine. That meant for us also to go for an ISO 27001 certification. So for those of you who do not know what it is, let me give you actually the history behind it, because it happened actually when I was at LIST. So back then, LIST signed the biggest public partnership, private-public partnership in the history of Luxembourg. I mean, back then, with Goodyear, 40 million euro deal to sponsor PhDs, postdocs, private RDI, and so on. First thing that they ask LIST, at least the head of IT, where is your ISO 27001 certification? We don't have one. Okay, fine, no problem. For every researcher working on a Goodyear project, here is a laptop. You have 2 years to implement it. So that, when we designed MeluXina, we knew it. So we said, okay, guys, we have to go. I mean, the company has to go for that certification. What does that mean in practice? First, we are yearly audited. We have auditors that sit in the company and go around everything that you do. So it means that every process inside the company is tracked. For instance, when I change position, in my former position, I had root access on almost all of the machine because I was managing the people managing the machine. When I switched to the application side, I lost all those rights because it's normal. I'm not supposed to have all those rights, so because out of separation of concerns. So I have there is a GitLab entry, removal of access for Francesco for local accounts on the machine. Everything is traced. We know who did what and so on. They check these kind of things. And so this gives you also I would say, an element of trust that is important for companies. Same for security. Security, when we designed MeluXina, it was not an afterthought, it was by design. So we went for set drives, so self-encrypted drives from really from the hardware point of view. And we're also in a tier 4 data center, which is, can feature a movie, because to enter that, you need to be Tom Cruise or something like this. So yeah, so it's a very secure environment. And yeah, and this is from the start, okay? So we are part of the EuroHPC family of supercomputers, because a couple of years ago, in 2017, 18-ish, the European Commission basically realized that they were lagging behind in terms of infrastructure compared to the US, China, and Japan. So they put a lot of money on the table, and they created the EuroHPC joint undertaking. Joint undertaking means that Europe puts money on the table, but the government has to put also money on the table, okay? So MeluXina is basically partly owned by Europe at 34.53% to be precise. And so on that share, they come with, it's open to the whole European ecosystem. So a lot of research come through specific calls that we have actually to technical review and so on. So the first call that the issue was for 5 petascale machines and 2 pre-exascale machines. So Luxembourg did not have a national supercomputer, so they went for the petascale, so the small machine. When I say small, we're talking about a computer of 30.4 million euros. So it's not that small. So we wrote that specification. So it was in between February 2019 and April 2019. And then so we got the co-financing, so 10.4 million euros. And then after, we had to work on the procurement for the rest, okay? So we are part of the EuroHPC network of compute. We're also part of the National Competence Center, because it's great to have such an infrastructure, but you need to make sure that the people can use it. So we are part with University of Luxembourg and Lux Innovation. We are the founders of the National Competence Center, where basically we give training, awareness sessions such as this one in the context of the NCC. Plus, we are heavily involved of the European Master for HPC. The coordinator is actually University of Luxembourg, Pascal Bouvry. So that is known as Mr. HPC in Luxembourg. He was obviously part of the original team that made MeluXina, by the way. It's a pan-European master program, so it means that you can start a year in Luxembourg and go 6 months at Barcelona, at UPC. And finish in Sweden at KTH if you want. Really nice, it's really cool. So we host a bunch of interns which are very, very nicely trained. So we serve research, obviously, public organization, and businesses. And since we started, we have onboarded 900 projects, different projects, and we have onboarded more than 3,000 users. And out of those 3,000, half of it is active on the system, okay? So that I already said, we guarantee high speed and so on. I will go in more detail, excruciating details actually, when I will talk about the architecture, but this is just a list of customers that already used us. So we go in Europe and beyond. Actually, we had in the early access in 2020, end of 2021, early 2022, we had the National University of Singapore also did some tests with us, SES obviously. And I'm going to show you some couple of use cases actually from them. It's very, very nice. And a couple of surprises as well. So just to briefly talk, so we are located in the middle of nowhere, Bissen, in the LuxConnect data center. So LuxConnect is in the business of data centers, and it's our mother company. And they have data center in Bissen, DC 2.1, and they have 3 in Bettembourg, DC 1.1, 1.2, and 1.3. And what is interesting, especially in Bissen, it's next to the data center, we have a co-generating plant, Kilowatt, that generate basically from waste wood, electricity, and also they produce cold water that is injected into the data center. So By the way, that data center represents an investment of roughly 80 million euros. It was built in 2012. And if you see there is like a grid surrounding it, it's a Faraday, because it acts as a Faraday cage to make sure that lightning does not strike the data center and it propagates internally. It's a tier 4 data center. It means that it's the higher availability you can get from a data center. Everything is doubled. So the power comes from 2 different feeds, and actually you see it in the data center. You have a feed yellow, feed blue. Water is also injected to multiple points from across the road, actually. And if there is a problem with the production of cold water, which comes at 12 degrees, on top of the roof of the data center, there is free cooling unit. So because we have quite a chill weather in Luxembourg, so we can actually reuse this to actually produce our own water, basically for free. So yes, and so power also, as I said, doubled. In case there is an issue, actually MeluXina is on UPS, by the way. There is, at multiple points of the data center, boat engines, okay? And they are, that were manufactured in the old Zeppelin factory in Germany, that are put on dampeners to make sure that the vibration do not propagate inside the room, okay? So they are really huge. And they have 8 of them. And on a monthly basis, they test them in case something goes wrong with electricity. Basically, if the power goes down, first the UPS kick in, and then after we go on diesel generators. It never happened in 4 years of production. Okay. Yes, I think that's it for tier 4. Okay, now MeluXina. So, in the world of supercomputing, there is a ranking, an international ranking called Top 500, which lists the 500 most powerful supercomputers in the world. So back then, the Ministry of Economy, they asked us, guys, we want you to be in the top 50. I mean, they went from not having national supercomputers and being amongst the top 50 most powerful machines. Okay, nice challenge. So when we rank the machine, you have the possibility to rank the machine twice a year. At the occasion of ISC, which is International Supercomputing Conference, which generally is in Europe. It happened actually last week in Hamburg, and they issued a new list. Or in November for supercomputing, which is the conference in the US. So originally we targeted November 2020, but due to COVID, everything was shifted. So the next, I would say, shot for us was June 2021. So me, when I joined, basically I said yes in October 2020, but I naively thought that the machine would be there by the time I joined in January. It was not the case, obviously. So I joined in January and there was nothing in the room. So we had from January until June to put that machine in production. So I lost a lot of weekends over that. But we made it. So when you submit your figures, you don't know how high you're ranked. So we were crossing our fingers. I mean, we knew we had a good machine, but we didn't know how well it would perform because you're competing with the rest of the world. So you don't know if US is going to rank new machine or China or whatever. So in the top 500, we ranked 36th most powerful machine in the world. So for us, it was mission accomplished because we had a goal to be in the top 50. But there are other rankings. Another one is the Green 500, which was important for us. Green 500 measure basically the efficiency of your machine in flops per watt, which is important. And there, we knew that we were going to be high. Why? Because we decided to go for a specific cooling technology called DLC, which stands for direct liquid cooling. It means that your CPU, GPU, memory, even your switches, network switches are liquid cooled. We're going to show basically behind the scene, you have a figure, an image of the rack that we have. It's very dense. I'm going to show you personal pictures that no one else except for my family have seen. And so we rank the machine, we give the number, so the HPL number, which is high performance impact. It's basically a set of linear equations that you have to solve through matrix factorization, okay? And there we were number 4 in the world and first in EU. So EU, I say EU because the Swiss had a better machine, but they're not part of the EU. So, I mean, jokes aside, we love those guys, the CSCS, because we're very fond of them, and we met them on a yearly basis because our technical teams go along very well. So we took a lot of actually inspiration from their machine. So Alps, the Alps machine, very nice, nicely done. So yeah. So just for you to understand, let me go back. I'm a first principle guy. So I will go back to the really, really basic of what is a floating point, because I thrown at you flops, floating point operation per second. But what is a flop? What is the FL stands for? Floating point. So you have to go back to the scientific notation, which came around early 20th century, where you have basically this representation of 1.3254, and you have this part called the mantissa and the exponent, okay? And the floating comes from the fact that your point will travel in a certain direction. It will float, basically, and it will stick to between 1 and 3, okay? So how this is represented in computers is through the IEEE standard 754. Here I show the 32 bits because the 64-bit would have been a bit bigger. So you have to understand why these standards exist, because back in the days, every constructor, old constructors such as Voxxed, DEC, IBM, they had their own implementation of their number representation, and it was chaotic, especially if you worked in science. If you wanted to use, I don't know, an SGI machine or a DEC machine, it came with its own representation of floating point. And then if you wanted to use another machine, then you had to rewrite everything. So it was a nightmare. So at some point, some bright professor at UC Berkeley, Professor Walter Kahan, said, enough is enough, we're going to make a real standards. And they issued that standards. And here, the representation in 32 bits, you have 1 bit for the sign, 8 bit for the exponent, and 20 bit for the mantissa. So you can compute how big a number you can actually represent with those bits, okay? So some people, especially one, John Gustafson, wrote 2 books saying we should basically stop using IEEE floating point standards because it's bad. So I will not enter that discussion. He wrote 2 good books about it. I bought them. It's convincing, but thing is that that ship had sailed a long time ago. Doesn't mean that we cannot do something about it. And people are actually doing something about it. They are basically using what he's proposing. So back then it was UNUM, but it's POSIT now. So it's an alternative which is compatible with floating point, but more secure, and which leverage really deep down parallelism. Because you at the lowest level possible, that standard basically prevent you to really leverage parallelism at that level. So it's really important to try to find something else. So a floating point operation can be any operation that you do on 2 floating points. So it can be an addition, subtraction, and so on, or a fused multiple add. So that one is more fancy. But you have instruction at your CPU level that do that, actually. Okay? So this is what we're talking about flops. In the case of an HPC, it's flops 64-bit, because scientific application require that level of precision. Okay? Now what you see with AI, especially with new GPUs, even in the data center, they remove FP64 part of their GPU to focus on the AI part, which does not require FP64. So now with the recent Blackwell chips from NVIDIA and even the MI355X from AMD, they start, not that one, actually the next one, the MI430, they're going to start basically removing FP64, which means that for us, for scientists, it's tough because it means that we have to try to find a way to reuse or to use such reduced precision to do actually scientific computation in 64-bit. It's really hard. It is doable by using mixed precision libraries and so on, but it's really hard. So just also to give you a comparison point for you to understand what is a supercomputer versus your laptop. MeluXina, the theoretical performance of MeluXina is 18 petaflops. So it's 10 to the 15. So it's millions of billions per operation per second. So it's a lot. A good laptop from that era, so I took 2020 as a reference because MeluXina technology came from 2020 actually. I took a good MacBook Pro M1, so nice chip, which, I mean, if you can, find the figures, so I did, and you have 1.3 teraflops in FP64, which is not bad. I mean, it's more than decent. So if you do the back of the envelope calculation, you end up with, you would need 13,000 ish MacBook to equal MeluXina. This is the theory. The practice is something else. And the practice is this. So as I said before, in the ranking, we use a specific software called Impact, so HPL, to rank the machine. And that software is meant to touch, or try to touch, the heavy-duty instruction of your CPU to do number crunching. So actually, we rank two systems, by the way. The GPU part, which is the most powerful one, and the CPU part. So there, if you combine those two numbers, you have a 12.81 petaflop LIMPAC. So you have the theoretical and the practical with that application, 12.81. So you see, you have some kind of a drop. That's fine. So if you do actually for Green 500, the ratio with the number of kilowatt that we use to do that computation, which is close to 400 kilowatt, you arrive at an efficiency of 26 gigaflops per watt. Remember, we're number 4 in the world. So I found the numbers of that MacBook. So someone actually ran HPL on that MacBook, and it got this number, 264 gigaflops. So if you redo your back-of-the-envelope calculation, it's not 13,000 that you would need. It's 48,000. So you see the order of magnitude. Why? Because your MacBook, your processor, even your GPUs and everything, if you combine every flop that you have in your MacBook, and you sum them, those instructions are not the same. I mean, there is a reason why a CPU in MeluXina cost back then 8,000 euros, because you have specific instructions that do not exist in your regular CPU or GPU for that matter, okay? So, and if you do, again, a back-of-the-envelope calculation, so MeluXina at peak consume 1 megawatt. So yes, it's a lot, but trust me, there are systems which will go way higher. And in terms of efficiency, again, we were very, very, very good. So if you sum up the watt used for that MacBook, we will end up with 3.1 megawatt. You see the difference? Okay, 3 times more if you would basically only buy laptops to do your supercomputing. The price, MeluXina 30.4. The price, so which I found back then was $1,500. So it equates to 72 million euros. So just for you to get, I would say, a sense of how efficient is that kind of machine compared to your regular laptops, and why we should not be building supercomputers out of laptops, because I'm not even taking into account switches and so on, okay? So because this adds up. I just put the flops numbers. So it means that 72 million is not actually reality. Versus here, everything is in there. What does that mean? Please do not throw your laptop, okay? Because this is actually a historical perspective of the performance in supercomputing land. And you see the increase since that ranking exists from the 90s. And if you take your laptop, and I always say to everyone, your laptop, so your today's computers is yesterday's supercomputer, okay? And this is really the reality. So if you had your laptop and you go back to 1996, that machine would rank 3rd in the world. And I'm pretty sure that the Sandia National Laboratory bought their machine for way more than 1,500 bucks, okay? But this is basically Moore's law hitting you in the face. And then are scaling, because if you see the numbers, the latest numbers, you see something very, very important. It starts to plateau. It means what? It means that we have many challenges ahead of us to try to do better. But so the free lunch was over since 2005. We knew it when we started to go parallel and multi-core and so on. But now we're hitting basically a hard wall in terms of what we can do with the transistors and so on, okay? So this is beautiful MeluXina with nice doors and so on. Grand Duke came, inaugurated it. I had the chance to do the visit and many more visits for high-stake people. But it's not MeluXina I knew. MeluXina I knew was like this. So we went into the room, nothing, really nothing. So we have a full room in the DC for us. And we started to receive the packages and so on. So it was in January 2021, and end of January actually, and it was in the middle of COVID, so everyone was at home but us. And then this is the air-cooled part, if you see the tiles. So this is the storage, that Christmas tree. So this is the GPU node, and you can see basically the cooling plates. So you have on the bottom the four GPUs, and if you really zoom in, you can see that actually the screws are green. That's how NVIDIA, how precise they are. And over there on the top, you see basically four other cooling plates. It's for the RAM, because the RAM is also liquid cooled, and the CPUs. Okay, and you have on the right, you see basically the network, the NICs, so which are special. I will talk about it in a few. And this is a CPU blade. So those are called pizza boxes because they are very thin, and you can rack them in a hot manner, obviously, in case you need to change RAM or CPU or whatever. And also you see all the cooling plate and so on. And on the GPU blade, you have one node per blade because the GPU takes a lot of place. On the CPU one, you have 3 nodes per blade. So it's very dense, okay? And those racks have a particularity that you can put nodes in the front and node in the back. So in a CPU rack, basically you can have 20 in the front, 12 in the back, multiplied by 3, you have 96 nodes in one rack. And we have 6 of CPU and 7 of GPU, okay? So high-level view, before we start zooming in again, we have 90,000 CPU cores across the machine, more than 800 NVIDIA A100 Ampere generation with 4 per node. We have in total 20 petabytes of storage, which is divided in multiple tiers. So we have tier 1 fast storage. We have there 649 terabytes of full flash. So it's very fast. We have designed it to go up to 400 gigabytes per second in read-write throughput. So in reality, we're close to 600. So we designed it for 400, but we got more. Tier 2, we have 12 petabytes, and there we have less throughput, or almost 200 gigabytes per second in read-write. Then we have the backup tier, 7.5 petabytes. And then located in Betambourg, we have also a tape archive, because for some projects, they're required by law to keep the result for 10 years. So we know that we had such case. So only tape gives you that possibility. So we started small actually for the tapes. We have only 5 petabytes, but we can grow up to 100 petabytes. We have the room for that, and you can basically extend the tape library for that. More than 450 terabytes of pure RAM, and all of this does not work without software. So when you log into MeluXina, I will show you after, you have access to a lot of software directly for you, okay? And it's very easy to use actually. So this is a 2.5D view of the room. So first, there is a lot of empty room. It's by design to basically welcome MeluXina AI. They're going to be co-located in space and in time. So when MeluXina will come, MeluXina AI will come. Today's MeluXina basically will be decommissioned if everything goes well in 2028. So by that time, the new machine has to be there and so on. So normally it's going to be there next year. So at the bottom, you see basically the liquid cooled part. So with nicely depicted with those wavy lines by the graphical designer. So we have 6 racks highlighted in red. So where you have 573 CPU nodes, 7 racks where you have 200 GPU nodes, where you have the 4 NVIDIA per node. So we still have also other type of nodes. We have 20 large memory nodes. So we knew that people were interested in doing in-memory computing, such as using Apache Spark when you have a lot of memory. So we put 20 nodes and each node has 4 terabytes of RAM per node. So it's a lot. And then we have specific accelerators that are not to be found in any other UHPC centers, FPGAs. So we are the only one with FPGAs in production. So this was asked by a local automotive company that are doing embedded system for automobiles, and they wanted to have a system where they could basically prototype their embedded system before they launch into production, before they launch into ASIC. You need to prototype. And FPGA, first of all, stands for Field Programmable Gate Array. Those are embedded, those are cards that you can program at a very low level. So you basically take your application and you synthesize basically the gates at the hardware level. So this takes a certain amount of time, but it's very efficient because you're really at the hardware level, okay? So very nice, cool piece of technology. We did many trainings. We have an in-house resident who is specialized in that, Emmanuel Kiefer, who did a training last week at the university, and I was with him to support him. And yes, and they use Intel One API. So it's a framework that enables you to use C++, a single source, and tap into, you can compile it to CPU, GPU, and FPGA. It's very nice technology. It presents you with specific models and so on. So now, this is the compute part. The storage part, as I already mentioned, we have 3 tiers. I will not go into detail for that one. We also have an on-premise cloud module with OpenStack. So to host long-running services. If you have a collaborative tool that needs to start a computation on MeluXina, you can host it over there. So we can give you Kubernetes clusters if you want. We have actually 2 of them. The first one, the original one, did not have GPUs. So it's CPU-only cloud. And now we have bought back a couple of months ago a GPU. We have H200 where you can host inference and so on. So next to it, we have also everything related to the external connectivity. So we have ISP-grade level equipment. We have probably the best connection in Luxembourg, at least. We're connected. We have 2 lines at 100 gigabit per second. We have connection to Restena, Géant, Lu6. We have also dedicated endpoints in case you want to avoid going through the public internet. If you want to connect to MeluXina without going, well, you need to be set up in at least in the data center. We can patch you to that switch if you want. And then we have a system module because you need to manage all of this. And this is a full job in itself because you have first thousands of machines that you have to manage, make sure that they are up and running, there is no issue and so on. But there is multiple networks inside. I didn't touch about the network. So the networks that you find in HPCs are not your regular networks. So we have Ethernet, obviously, but it's actually 4 networks that you can find. You have the management network, the data network, the BMC network, and the high-speed interconnect network, which is, in our case, called InfiniBand. So InfiniBand is a really interesting piece of technology. It was designed by Mellanox, which were bought by NVIDIA a couple of years ago. And I would say the main difference between a regular Ethernet and InfiniBand is that a node can read and write into another node's memory directly, okay? This is without going through the OS and so on. You can bypass the OS and read and write directly into the memory of the other node. But for that, you need to use a specific library, okay? Actually, a specific driver called MOFAD, but MPI, Message Passing Interface, to leverage that. It's very powerful. This gives you very low latency and super high throughput. So the one that we have is 200 gigabit per second card. So for CPU, we have only 1 NIC, but for GPU, to feed those beasts, you need 2 NICs. So we have per GPU node, 400 gigabit per second for the network. So it's a lot. So they're very powerful. So the system module, as I said, we monitor also the pressure in the cooling loop, because in case you have a leak. And when we started receiving MeluXina, we had false positive. And so we didn't know if it was real or not. So we did a couple of runs in the data centers to make sure that we did not have leaks, because having leaks in such a system can be catastrophic. So we had to basically adjust those thresholds and so on. And then, because we did not have monitoring in place back then, so we started to put monitoring in place, because after we start checking the pressure as well, because if you had basically a leakage event without the corresponding significant drop in pressure, it means that it's a false positive, okay? So, but still, we managed to run a couple of times in the data center. Yes, so the tape is in Bettembourg. So LuxConnect, as I said, they are into data center, but it's half of the story. They're also into dark fiber. So dark fiber is they have 2 dark fibers, one following the highway and the other one following the railroad. dedicated between the two data centers. They can operate each other in case of an issue. And we connect it through active equipment, so namely the ADVA, through the data center to basically make sure that we have a specific path to do the backup, okay, using that channel. So all of this does not work without software, and we have a lot of software that my team manages. So software starts from compilers. So we have AOCC, which is the AMD compiler, GCC, which is the GNU compiler. We have the NVIDIA compilers. So back then, NVIDIA bought a company called PGI, and so in those days, yeah, I sound like an old fart, but in those days, you had to buy your compiler. It was not for free because some compilers were emitting really good code. And it was the case, for instance, for Intel. So they had the Intel, it was called back then Parallel Studio, Cluster Parallel Studio. And I think a license was back then 10K a year. But the code was really good. I mean, the emitted code was really good. And then after they released it for free. NVIDIA bought PGI, and now basically they release all the compilers that came from the PGI group, because we had PGI and Intel, and we had the license, yearly license, and now it's not the case. So now basically it's free. It's actually, for that is great. We support various programming languages, including Python, R, Go, Rust, and so on. So you can simply, I will show you after how easy it is to load a module and use Rust, unload it to use Python, multiple versions of Python, because we have multiple stacks which lives in parallel, and you can jump from one stack to the other, and all the dependencies are managed for you, which is awesome, because if you are doing really low-level software programming, then you know that you have to suffer through environmental variables and these kind of things. We do that for you through a specific system that we call EasyBuild, but I'm going to show it after. We have performance debugging tool, because you want to understand that this is something that my team does. We do but basically what we called performance debugging. So performance debugging, they give us a code, and the user is not happy with the performance of his code. It's running slow. Can you help me out? So what we do, we use profilers that give you, I would say, a feedback regarding the performance. For instance, you are not using the SIMD instruction, so the really low-level instruction that enables you instruction-level parallelism, and so on and so forth. Or you're communication bound. So it means that you have to improve the way your computation is distributed, and so on and so forth. And we have multiple profilers that we use, actually. We never use only one profiler. We use a combination of profilers because they all have their strength and drawback. Then we have the ones also from NVIDIA, the Insights. Were very nice because they give you really the low-level details of what's happening on the GPU, okay? VTune and so on. So then after, we have the parallelization tools, such as OpenMPI, Intel MPI, the TBBs from Intel for the thread building blocks. Those are libraries, C++ library, to enable you to write parallel code, okay? cuBLAS, cuFFT, those are CUDA libraries for basic linear algebra, for fast Fourier transform from deep neural networks, and so on. Same for FFTW, so those are fast, it's an acronym for fastest Fourier transform in the West. So a lot of, if you do a lot of physics, you have to do a lot of calculation using complex numbers and these kind of things, and fast Fourier transform can be useful over there, also for signal processing and so on. Then you have the Boost, Scalapack, HDF5 for hierarchical data format. If you want to bulk a lot of pictures into one binary blob, you can use HDF5 for that. And then up to the frameworks that you probably know, PyTorch and so on. So PyTorch, they rely a lot on those low-level libraries. So you, if you want to train a model, an AI or something like this, you will use PyTorch in 95% of the case. A couple of years ago, it was not the case. It was TensorFlow, which was the cool kid, I would say. And those frameworks, they have a lot of dependencies, like a lot, and sometimes in the hundreds. And if you miscompile one, it has tremendous bad effect. So, and we make sure that we have the good flags to compile PyTorch, Torch, because PyTorch is just a wrapper on top of it, which is Torch is a C++ code. Rapids AI, so from NVIDIA. So Rapids, I'm going to discuss it later on, but it's a collection of frameworks from NVIDIA to do data science on GPU. It's very cool. And so on and so forth. You see Apache Spark, obviously. We have also quantum simulators. So we put that over there to start to design and understand how to go from classical computing to quantum algorithm, basically. So this is very interesting. And we have simulators. You can simulate that on GPUs and CPUs if you want. And then we have end-user application to do molecular dynamics, computational fluid dynamics. I don't know if you probably saw that on TV and so on. When you want to evaluate the aerodynamics of a sports car, they put that in the wind tunnel. So wind tunnel is very expensive, but you can do that on a computer with what is called computational fluid dynamics. And it's a very important field in science, actually. And yeah, to make sure that you build the best car in the world or the best Formula One. Formula One is a big user of HPC, actually. They have limitation in terms of flops per year that they're able to do, actually. It's very, very interesting. So yeah, so all of those end-user applications are used for that, for drug discovery as well, for doing molecular dynamics. So how the atoms interact at that level, how I don't know, carbon interact with silicium and so on, at that really atomistic level. You can simulate things that do not exist in terms of materials if you want. That was at least what my colleagues were doing. So all of this, I mean, you as a user, you don't interact directly with the HPC. In a sense, you interact with it through a scheduler. And the job of the scheduler is to optimize the placement of the job. So when you want to run an application on 10 nodes, for instance, you want to make sure that the nodes are next to each other to minimize the latency between them. And Slurm has multiple internal scheduler to help you to do that. So this is what you see on the right. It's a Slurm script. And the -s batch, those are called the directive that for the Slurm scheduler. So here I said my job name is going to be this. The account, because it does accounting, so it's the project name that we give to the user when we onboard you. The partitions, because we have large memory, CPU, GPUs, and FPGA partition. The QoS, the quality of service, that is applied. So here it's the default, but we have short, urgent. If you do really need to compute for urgent matters, we have a specific QoS for that. Interactive as well, if you want to do interactive stuff. And the number of nodes, the number of tasks per node, the wall time. So the wall time is how much time you're going to give me those nodes for. And then at the end, you start to load. So the module load is to load up your software. I'm going to show it after, actually. And then after, it's related to the execution of your program. And you see the srun stands for Slurm run. So it's a wrapper of MPI run to launch your application using MPI. And the GMX is for GrowMax. GrowMax, you may never heard of it, but without that tool, vaccine, and especially COVID vaccine, would not have existed, just for you to understand. That software is incredibly powerful and used throughout the world. I happen to know, so one of the person behind it, so he's a former professor, he's a professor at KTH where I studied. So very cool software. Very, very important software. So as I said, we are very much into security. So to connect to MeluXina, you have to use elliptic curve 25519 keys. Okay, no RSA. Only those to access MeluXina. We used anonymized account because the user should not know who is on the machine. So Goodyear should not know that Michelin is on the machine. Okay. We have authentication and authorization rules. On the login nodes, we have ACLs in place. You cannot see what's in the queue because the scheduler has a queue of the jobs that are in the queue. You cannot see what is in the queue. So it means that you cannot see that Michelin has a brand new software called something and they are doing some tests, okay? And it's again by design. What we do is before we provision the nodes, so the nodes are diskless. So it means that the OS lives in RAM. Before we give you the node, we scrap everything. We give you the node, and after you leave the node, we scrap everything. Because it's in RAM, it's super fast. So we do PXE boot in 2 steps. The first step goes through the initramfs for the geeks among you. goes through the gigabit Ethernet, and the rest goes to the image itself of the OS. And we use Rock Linux, by the way. It's provisioned by the InfiniBand, so it's really fast. And also something which the other centers do not do, we do full node allocation. It means that you are alone on the node. We don't do node sharing, which is a pro and con. Pro is security. So it means that if you have another user, it cannot do side channel attacks because you're alone on the node. The con is that we cannot maximize utilization. So it means that if a company, an organization wants to use MeluXina and the developer is only using 2 GPUs out of the 4, you can have another user using the 2 other ones. So this is, technically it's possible, but we did not put that in place for security reasons. We try to promote security more than the rest. So security, as I said, encryption at the hardware level, and we have also a very nice feature called root squash. So even if a user would acquire pseudo privilege, he cannot see the data of the users. Is being root squashed. So there is an active mechanism that track root escalation within the nodes that prevents you from seeing that at the file system level. You can only do that through dedicated nodes on MeluXina, and only 4 people within the company have access to that. I used to be one of them. I'm not anymore because I changed position. But yes, only a handful of people can go through specific nodes which are completely secured and so on, okay? So how to load software? So this is something that I discovered when I started managing an HPC. So I come from the distributed computing world, and the HPC is an instance of it. But I come from the peer-to-peer world, actually, and the big data world, so to speak. So when I came on an HPC, first of all, I still use Fortran. I was like, yeah, okay. So yes, Fortran is very used, actually. And if you watch your weather forecast in the morning to make sure that you don't get wet and so on, 95% chances that it ran using Fortran, because the old weather forecast models have been coded for many years, and they're still there. So I had to debug Fortran code. It's an experience, but it's a language that evolves with time, by the way. It's an ISO standardized language, and the last standardization actually from 2023, and before that it was 2018. So they had new features, actually, so it evolves. The same with C++. If you had to code C++ before 2011, it was a bit painful. 2011, it was really a big change at that level. So they put a lot of things like resource acquisition, initialization, these kind of things. So it was really a change. It was a new language, basically. And then they tried to do that also with C++ 14, 17, 20, 23, and the rest, okay? So, but this takes time. That's why the Google-like of the world, they go for their own language because they don't want to wait for new features. But it takes time for good reason, because as I said, we have a lot of legacy code that is still out there on which the world relies on, including the weather forecast and the climate stuff, okay? So you cannot change put a new variable, a new keyword for C++. You're gonna basically screw up billions of lines of code at Google, for instance. So they cannot allow you for that. So they're part of the ISO committee. So I'm sorry, I do a lot of digression, and I'm pretty sure I'm not done with the digressions, but okay, we'll try to stick with me. So module is something, as I said, discover in HPC is to load and unload modules on the fly. And if you allow me, actually, let's go on MeluXina, because otherwise it's boring for you. So I'm gonna go, let's go here. I'm gonna go first, there are multiple ways to enter MeluXina. I'm showing you the old way because I'm old. I don't know. So I still go through terminal. So when you go on MeluXina, you land up on the login nodes. And the login nodes has a nice message of the day. First, a recap of the what's in the machine, and also system events. In case we have a maintenance which is planned, you can see it over there. We have many mechanisms. We have the website, we have the Jira service desk. So we put the fact that we're doing a maintenance everywhere to make sure that you do not, you cannot say, I wasn't aware. No, you can actually. So here I'm on the login node. So first module is not available on login node because to make sure that people do not launch computation on the login node, which happened. We had a customer once, it's a small anecdote, that he was trying to make a point, I don't know for what. He had a node, so a GPU or a CPU node, and at some point he was not happy with the performance of that node, and to prove his point, he ran on the login node and had great performance because the login nodes are really beefy nodes. We have 128 cores on those nodes. And say, hey, look, you see, the login node is way better than the compute nodes. They say, look, I mean, I see the point you're trying to make, but please avoid that because you're impacting the users. Because you're not alone on the login nodes, you have many users. So please avoiding that. So yeah, you had to stop that. So here, so I created I would say aliases, but I would say if I do, and I grab, give me. So here, those are the aliases. So because as any good software scientist, I'm lazy. So if I want a GPU, I say, give me GPU, and I'm going to get a GPU. And behind the scene, this is the command that is basically running. srun -a for LXP, it's an account, because we have to keep track of what you have used, because after we bill you, because it's not for free. And then all the parameters here, for instance, -p is for the partition that I would like. So I want the GPU. I want only one node. I want 4 GPUs on the node. I want for 2 hours. I disable perf paranoid. So who of you know what is the perf paranoid stuff? Okay, perf paranoid is basically if you want to get the performance counter from the CPU to get basically an indication how, I mean, the profiler needs to have that to sample the application to make sure that, okay, this is your bottleneck and so on. And you need to have to basically take what is called the IB, the perf counters. And you have to enable a specific flag at Linux to enable you that. And forwardx if I want forwardx. So if I want a CPU, okay. So here, so first it's alive. It's live demo. So if it goes wrong, it goes wrong. I'm sorry. So here up, I was allocated a node. So I'm on mel 06169, sorry. So naming convention. If a node starts with 0 on MeluXina, it's a CPU node. If it starts with a 2, it's a GPU node. If it starts with a 3, it's a FPGA node. If it's with a 4, it's large memory node, okay? So that's how, because we have thousands of machines, so we have to make sense of it. If we allow random nodes, we don't know where we are. So here, let's say that I want to use GCC. So if I say, okay, GCC version of the system is, so of the base image is 8.5.0. And if I want to load,
sorry.
Yes?
You just said that if it starts with 3, then it's a
FPGA.
FPGA, but you asked for a CPU here, right?
Yes? Yeah. I didn't ask for FPGA. It was just to...
Yeah, but then it starts with 3, right?
No. You mean in this thing?
Yeah.
No, this is the job ID. So what I'm saying, the name of the machine is this. Mel 0169. Sorry for the confusion. No, the job is the job ID, which is a unique ID that when you ask for a node on Slurm, it gives you a job ID to reference the job. Okay? So now I loaded a new version of GCC, and if I do this again, I have GCC 13.3.0. Okay? And so if I do module list, it's going to basically give me what I've loaded in terms of module. Okay? So if I do, for instance, Python 3. So you see the base is 3.6.8. Okay? And let's say that I want to load new Python. Okay, if I do tab, there is tab completion to make sure that we have, and if I load the regular one, let's load the regular one. And if I do Python 3, and normally I should have the 3.12.3, you see? So this is how I can load on the fly packages. And you have many packages because many users use different. So here I'm basically, and yeah, interesting stuff as well. Let's say that I load packages, Python and so on, and I say, crap is the wrong version, I want to go for an older version of Python, I can change stack on the fly and look what will happen. So here I'm gonna go and load another version of the stack. So there is release stack and staging stack. And I will go for 2023.1. So we name stacks. And if I do that, look what's gonna happen. It's gonna reload and tell you, I switch GCC 13.3 to GCC 12 because the old GCC was part of the stack. Same for all the dependencies. And now if I do Python again, Python 3, sorry, what do I have? Python 3.11, you see? On the fly for you. And also an interesting, I mean, if you want to know more about what it's actually doing, if you need to have access to environmental variables and so on, you can do module show, and it will give you everything that it does actually for you. It's prepending the path, see make prefix, it's prepending the path that we used to do manually, and it's setting up a bunch of paths for you, okay? And this is where you can find actually the application and all the libraries and so on, and all the include. I mean, if you need to compile against a library, okay? So, yes, I'm gonna exit now. Oh yeah, by the way, let's see if something still has this effect. So here I'm showing the tier 1 and tier 2. And yes, here the P is for petabyte. Okay, so I don't know if you're used to it, but yes, so it's real. I mean, oh yeah, by the way, I didn't mention actually what the file system is. The file system is called the Lustre. So Lustre is a distributed and parallel file system, which is POSIX compliant. So if you're into big data, you're used to HDFS and so on. HDFS is not POSIX compliant. It's only append only. It's immutable. So you load, I would say, a base data set, you load it in the HDFS, and if you do modification on it, you have to append it. This is not the case on an HPC, obviously. An HPC is your regular Linux XTF4, except that is distributed with metadata server, block system, and so on. It's really big. And the name is called Lustre. There is multiple ones. There is GPFS. No, it's now called SpectroScale at IBM, or even they change name. Every now and then they change name. So I used to know it as MMFS, so which was the multimedia file system. Then there is also FSGFS, which is the Fraunhofer file system that changed name. Now it is BGFS, and so on. So here I'm gonna quit. Okay, so now I'm back on the login nodes. And so this is one way to access MeluXina. I will show you a nicer way. Is through something that we've recently deployed called Open on Demand. So Open on Demand is a portal where we can deploy application. And here we have, for instance, Jupyter notebooks, desktop. We have Blender, we have ParaView for visualization, and so on. So already I think, just to make sure, because I didn't want to book nodes only for me. I don't want to penalize the customer. But I wanted to make sure they had a node. So here, for instance, I've launched a desktop application on MeluXina, and now basically I can go to MeluXina. And here, so here I'm on a node, and I'm on a GPU node, I think. Let's check. Yes, I'm on a GPU node. And if I want pop CD, let's load something up. Okay. So I'm going to show you something. I hope that you will find it interesting. So it's not big data yet, but bear with me. So this is a fluid dynamic code. Let's put it on 0, which is running on the GPU. Okay. So this is running live. Up. So let me pop. I'm going to do this, this, and this. So this is a fluid, basically a fluid dynamics. So it's a delta wing. It's not really something fancy, but you can change the STL. So if I want to put a Ferrari or a Lamborghini, I can put that in there and set it up so I can basically visualize the turbulent flow or the laminar flow. So in fluid dynamics, you have two types of flow. So fluid, laminar one, which is really steady, and turbulent. And if you have planes and so on, you want to avoid turbulence at the tip of the wings, okay? Same for a race car. So if you put a Formula One, so Formula One first is the worst possible car in terms of aerodynamics because they would go faster if they had like a proper, how you say, carrosserie, I forgot. But if they had basically, if it was like the Le Mans series, they would go even faster. But they cannot for regulation. And but they put a lot of little wings here and there to improve the aerodynamics. And this is how you basically can simulate using this kind of tools. So this is one tool called FluidX3D. So the person behind it was a PhD student in Germany, and now he's at Intel. Okay. So again, this is live. Huh? I'm not cheating. It's not a video and so on. This is really live, and it ran on the. So it spit OpenCL code on the GPU. Okay. So yes, you can also run containers on MeluXina, but not Docker. Why? Because Docker does not support InfiniBand. So it means that you cannot leverage the high-speed interconnect. But there is a nice alternative called Aptainer or Singularity, which is 100% compatible with Docker. So it means that you can pull any Docker, okay, put it on MeluXina, extract it, and use Singularity runtime as a container runtime, okay? And you will have access to the InfiniBand. It's really neat. So you can bring your own software stack. Chances are that it will be less efficient than what we have compiled, but you can still bring it. So I'm gonna digress another time. I'm sorry about that. So scientific computing is something which is at the center, at the crossroad of three fields: computer science, obviously, your engineering problem. So it can be life science, it can be environmental science, and so on, and mathematics, okay? So just a quick reminder for you guys. So a difference in terms of approach when you try to solve, or if you want to compute something, you have two approaches, either the numerical one or the analytical one. So let's say that I want to compute the sum of squares from numbers from 1 to 10, okay? So a simple one. The numerical approach is I take those and I do the computation. I do one square plus two squares and so on. I unwrap it. I do 1 multiplied by 1 plus 2 multiplied by 2 and so on and so forth. So what does it mean in practice? I have n additions and n multiplication. And we say that the algorithmic complexity is O to n. And for practical purpose, we said the 2 doesn't count. So it's in the order of n. So if you have n equal a billion, then you have to do a billion of those, 2 billions of those computation. Okay, this is the numerical approach. Now, every time if we have an analytical solution, we will go for it, okay, because it's way faster. And just to give you an idea, this is the formula that you can use to do this same computation. So n multiplied by n plus 1 by 2n plus 1 divided by 6. You have 2 addition, 3 multiplication, and 1 division. And you have only 6 basic operations, regardless of n, okay? So this will go way faster, okay? Obviously. But unfortunately, life is cruel, and we cannot have analytical solution for every problem. And this is one of them, an important one. So who of you know what kind of equations those are? Try to guess. Nope. Nope. Anyone? Those are Navier-Stokes. Navier-Stokes equations are the equations that capture the behavior of fluid. So as I said, fluid is a very important field in the world, actually. So aerodynamics of car is one thing, but if you want to simulate tsunamis, or if you want to simulate, the weather is a fluid. It's air, it's water, and so on and so forth. Okay. If you want also to simulate how the blood goes into your organs and so on, you're doing hemodynamics actually. So fluid is really important, and those equations govern basically fluid dynamics. Okay. And those equations are used, for instance, here on top, I've used it, actually it's a software from NVIDIA called Earth-2 to simulate, I think it was humidity around the globe. So it's purely on AI, okay? But here, the cooling towers, so I put them, why? Because next to it, you can see some patterns, and the patterns are called Kármán vortex street. It's something, if you have a pole and you have a lot of wind, behind the pole, it will create a lot of turbulences, okay? And this, if you have a strong wind, you can break those cooling towers. It happened actually in the 70s in the US. Yeah, I don't think there was any damage except material, but this can be devastated for companies, factories, and so on. That's why here, you see, you have those fins. Those are called rakes, and to break the turbulences behind the pole. So, and this is actually a picture from the ISS of an island, of a Japanese island, and you can see those Kármán vortex streaks actually happening in real life. Okay, and over there you have, when a fish swims, it also creates this kind of turbulence behind it. Okay. So this is another set of equation. So who of you try to have a guess on this one? So what? No, this one is actually n body. So the n body. So for the people who have watched the series, there is a nice series called the 3-body problem. So where they say that you cannot solve the problem. No, you cannot solve it analytically. You can solve it for 2 analytically, but not for 3. And it's true, huh? This is true. But you can solve it numerically, okay? This is the part they always omit, and it pisses me off. Because you can solve it, because otherwise we would not be able to send rockets, space probe in space. Actually, if you have seen The Martian, the movie, at some point, they forgot the poor guy on Mars. And there was a brilliant engineer who said, actually, he had like a breakthrough. And then he runs to the data center, compute basically the trajectory, and said, because of the positioning of the planets, you can actually go back faster. Why? Because he's taking basically what is called gravitational assistance from the planet. So if you have a space probe, so here, those equations are used to compute also trajectory of space probes, as I said. And here is the case of a space probe called Cassini that was launched in '97. So Cassini was supposed to, not supposed. It went for studying Saturn and the satellites of Saturn, okay? So when you launch, that's why you launch at specific point in time, is due to the planet's position in space, okay, and in time. And this is what they compute on a supercomputer. First you launch, then you go for Venus, you go around Venus, and not too close because you will be attracted to Venus' gravity, and then the probe will and explode. But you will compute and try to leverage the gravity of Venus and go whoop faster, like a slingshot, basically. And they do that multiple times. So one time around Venus, another time around Earth, another time around Venus, Venus 2. Then after they will shoot for Jupiter, because Jupiter is positioned over there, fly by, and up there they can still do course correction. They do course correction actually. And then after they shoot for orbit insertion, so to make sure that they go around Saturn. And then they launch the Huygens probe on Titan. NASA did a beautiful animation on that. It's really great. This is what they use. And you see the G is for also the Newton's constant, or gravitational constant. We still use Newton's mechanics for that, not relativistic one. Why? Last time I checked, a planet does not go at the speed of light. So Newton mechanics is still good enough for that. It's not good enough if you want to study things at the atomistic level, because there the particles go very, very fast, and Newton is not enough to capture that. But it's still good to capture the trajectory, to compute the trajectories. So it's still Newton mechanics behind the scene, actually. Okay, so do you know which beautiful equation that is? That one scares a lot of people. It's only a partial differential equation. This one is Schrödinger's equation. So not the cat, please. So it's the same guy, but so this equation is used in material science. So because you want to compute things at the quantum level, there you can do what is called ab initio simulation. Ab initio means in Latin from from start, from scratch. So in Italian, inizio is the start. So you do basically simulation from the start. And in a theory called density functional theory, which is based on statistical mechanics. I will not go into that one. It's a beautiful theory that is used, and actually is by my former colleagues at least, to create composite material. Okay, so when they come with a new nano powder, which is super for coating satellites because it's absorb light and so on, they run such simulation using basically solving this equation. I mean, they're solving instance of that equation, okay? Same for theoretical chemistry. You use actually those methods to compute new drugs, new molecules that will make up your new drugs and so on, okay? So mathematical interlude, Schrödinger himself was not pleased about that little I in his equation because it's a complex number. So, so he was not happy and he wrote a letter because that's what scientists used to do back then. They wrote letters of anger. I'm not pleased to his friend. So I here, just a reminder for I mean, it's old, you learn that at actually a high school, but so complex numbers have a great history behind the scene. And I urge you to go and watch that beautiful video from Verasium, which is really good at explaining such things. And so the reason of the existence of complex number in the first place was to solve what is called depressed cubic equation. So when you have basically x to the power of 3 without the x to the power of 2 term. And then after it was refined and to basically solve this kind of equation because they had no solution. And basically you will find out when you do this kind of computation, and when you roll the computation that they cancel each other and so on and so forth. But I will leave you that for another time. So we also dabble obviously with AI. So personally I was involved in this project called LlamaFile. So I don't know if you know about that. So it's a project from Mozilla Research, and especially from one engineer, Justin Tunney, a great engineer, was formerly at Google, and she took up that project. And when I say she's good, she's very good. She came up with her own compiler called Cosmo CC, with a way to do portable C actually. And so she applied that to LlamaFile. So LlamaFile is basically your LLM web app plus the model in one file. Okay, so it's very easy to actually deploy. So you take one file, if you want, you go on the GitHub, and they have models where you have Mistral, Quen, and so on. You take it's only one file, you put execution flag, and you change the permission, and you run it, and you have your AI. So it's very easy to use. And they launched a discussion online, so discussion 450, where they wanted to benchmark different CPUs. And I was curious, I said, how do our CPU compare? I mean, we have great CPUs. I mean, they must be good. And I did. So I uploaded my numbers, and on our CPUs, I'm with Mixtral model, so it's the 7 by 8B. I managed to have around 240 tokens per second on CPU. I mean, which is not bad. We have over 573 nodes full of CPU. So it means that you can actually do inference on those CPUs as well. So CPU is not dead yet, guys, by the way. And we're also having fun on FPGAs, but this is more advanced. Also, something which we see in the AI world is that users leave a lot of performance on the table. So this is an extract of a real ticket. So at some point we did a maintenance and we updated Slurm version. And sometimes out of the blue, because we cannot catch everything, Slurm changed a flag to run the computation, a specific flag that had to do with I think it was about yes, it changed the name actually of the flag. So they changed it. I mean, no, it was a CPU end task, the end tasks. And so he was complaining, my workload goes twice as slow as before it used to. So, okay. So we checked, and actually he was right. Okay, yeah, indeed, the flag is different. So now we use that flag. But then I got curious. So he was doing face recognition on CPU. Don't ask me why he was not using CPU, GPU, but okay, fine. I'm not here to judge. So what we did is I checked his code with his permission, obviously, because I had to investigate his initial error. And then I saw this line. So the engine. So as soon as I see an engine instance, a class instance, I say, can you do better? I'm pretty sure behind the scene, you can do some stuff to improve it. So first of all, I checked his batch size, and his batch size was really slow. Why? Because people have weird behavior when they come on an HPC. They think it's their laptop, but no, it's not their laptop. You can increase your numbers like crazy if you want. So I immediately did it. I took his batch size and multiplied it by 4. Okay. I took the number of cores. You can parameterize actually the engine, and I matched the hyper-threaded version of the CPU, so 256. And then I use a multi-stream scheduler behind the scene, and I said the number of stream equals to 8. Why 8? Do you have an idea of why 8? I'm showing off here a bit, but the 8 has to do with the architecture of your CPU. So the architecture of your CPU, you have on the 7H12 AMD EPYC, you have 8 NUMA domains. So NUMA domains, this means that the core are split it in 8. Okay, so you have 16 cores per NUMA domain. Okay, so I did that. So I changed only that line of code, and I changed the way to run the code. And I said, look, in order to avoid what I call the dancing thread effects, dancing thread, it means that the threads are changing from one core to the next. And this has a bad effect because the coherence protocol kicks in and it's bad. So I said, no, the threads will stick to the core. Don't move, guys. Stay where you are. Compute where you are. I use NUMA control for that. So I physically bind the CPUs and so on. And I run this thing. So I change this line of code to match, to bump up the numbers and to match our CPU architecture, and I change the way to run it. And I immediately gain 8x. He was leaving 8x on the table. So I managed to go 8 times faster. You know, I have histories of this kind of behavior, okay? And this is getting worse with AI because people use PyTorch, they run it, but they don't care about the performance. You're paying for compute time here. If you can go 8 times faster, it means that you're reusing 8 times less the resources. So you should care, okay? So scientific program, I'll try to go fast. So the lesson here that I would like to convey is know your hardware. The hardware has specificities in terms of L3 caches, the memory, the channel, the bandwidth, and so on. This is true because for CPU, GPU, and FPGA. So you see also the TDP is different, a bit different. I mean, the A100 are still okay-ish, but the next generation GPU is going to be insane. So you have to make sure to use those well. And this is my message here, okay? So we understand that it takes some effort. If you have a CPU-only code, then use the CPU, but try to leverage all the cores that you have. Same for the GPUs. If you have a GPU-oriented code, try to use the 4 GPUs that are in your machine, okay? And the same for the FPGA, but the programming effort goes a bit up. But we are there to help you out, okay? So again, to show off, so generally I ask the question, what is the type of the CPU? And generally people cannot answer. So the type of the CPU is an out-of-order superscalar with speculative execution CPU. It's a mouthful, I know, but out-of-order means that the instruction that your CPU is running, they do not run in the way that you think. So the fetch, decode, execute that happens at the CPU level is not happening linearly, okay? It's happening at the best possible way. Superscalar means that you have intrinsics. So you have instruction level parallelism, which means that you're not fetching one data, you're fetching a whole cache line of data and run it in parallel, okay? This is called SIMD intrinsics. And those CPUs, they have specific ones. So you used to call them, Intel used to call them SSEs for streaming SIMDs. MMX, for the people that are really old, you had the Pentium 2 MMX. The MMX was an instruction for multimedia decoding, okay? So then you had SSE 4.1, 2, 3, now you have AVX for the vectorization and so on and so forth. Those are called this is for the superscalar part. Okay, and you have to leverage those because those, it's really, you can leverage parallelism at a really low level. So, and you have to understand how it works behind the scene. I know it's a lot. It's our job to do that. I mean, don't be scared. But we help you out. So this is what the people in my team know and do whenever they touch code, scientific code especially. So they know the prices of different instructions. Not every instruction has the same price on a CPU. Some are slower. For instance, anecdote from the past. I used to compile an application called VASP for ab initio simulation for a material scientist. And we had Intel Skylake 6350 CPUs. And there you had AVX 512. So it means parallelism on 512 bits. And for some odd reason, I mean, the scientists thought that by generating more AVX 512, it would go faster because it would leverage parallelism. And the intuition is right. But what he did not know is that those instructions are throttled, which means they do not run at the max frequency. They run at lower frequency because otherwise your CPU will burn, okay? So this you have to know, the internals of a CPU, to avoid making that mistake. And I had, to convince him, no, you should stick to AVX2. Do not go AVX 512 because you will suffer from performance degradation. And I proved him right. So I had to do benchmark and I proved him. So do you know who his beautiful old man is? So that person, you have know his name, is Amdahl, Gene Amdahl. He used to work at IBM, and he was actually behind this IBM 7900 line that was used also to compute the trajectory of the Apollo mission, okay? And that guy, he built computers, but he built also the software for that computers, which was already parallelized back then. And he came with his law saying that, by the way, your software is going to be restricted, you're going to bottleneck on the serial part. No matter how many processors you throw at it, you will never go fast. So, okay, but he had an assumption, is that the problem, the original problem, was fixed, which is not the case. I mean, the original problem, you can throw more data at several versions of the problem, okay? Which is not the case. He did not have in mind that. He had. So he said, hey, by the way, I will going to refine your law, and I'm going to say, yeah, you have to account for the workload at hand. And I met this guy actually last year, and he's one of my heroes. Both of them are. And he improved it again, taking the coherence protocol in basically when the threads are communicating, there you had an overhead, and this function captured that. So this is for you to understand, you have limits at the algorithmic level as well. So keep that in mind. We have to keep that in mind when we do that. And this is a lesson from I would say, a lesson from the trenches, that people at MIT, they realized that, and they came with a beautiful paper that won the best paper at this conference. This conference is the top notch of all the conferences in computer science. It's called SOSP, and the scalable commutative rule basically states that if your operations are commutative, basically there is an implementation that scales. And they apply that to a microkernel called XV6 that is taught at MIT for all the undergrad. And they managed to create a microkernel which scales very nicely. And their paper shows that. Me, when I read that paper, I said, I'm going to apply that also, that rule, to scientific code. And that's what I did, basically. And I basically, if you follow that rule, you're going to make applications that scale. It's really hard, but you can do it. And I did. So I basically created so I implemented something. So the gentleman on the left is, he was a former colleague of mine, and he's next to what is called an anaerobic digester. So that thing stings like hell, like literally. I mean, so there they put, all the basically grass and so on, and to create methane. It's to basically create a methanization mechanism. And they wanted to improve the efficiency of the biogas reactor, is to create biogas from waste, basically. And and they wanted to identify the most efficient bacteria which produce the gas. So what they do, they sample every month, and they run a specific clustering algorithm called co-abundance, and k-means and so on. And the first part, so this is real data, okay, by the way. And so it doesn't look big, but the computation is big behind because of the algorithm itself, because you have to basically compare all the DNA pieces called context together. So they had an original implementation that took 5 minutes. So you say, it's not that big, 5 minutes. But as soon as they increase the number of contigs, that thing would blow up. They said, no, I'm sorry, if you go to 80,000, I cannot do it. So I had to re-implement it. I implemented it in different languages. And then I implemented, so it was in 2014, in TensorFlow on GPU. And I went from 5 minutes to 0.15 seconds. So almost 2000nx. But my implementation scaled. So it means that you can throw 80,000, it's going to scale linearly. Okay? Same if you put even more context and so on, it's going to scale linearly. So that enables them to go at scale. Okay? And a funny story that you get when you're working with real scientists, biologists, they went to the French Guiana and find out a termite which is the best as digesting specific lignocellulose. Okay? And they brought that back. And we did a paper together. It was really fun. So this is the implementation. So I used NIM back then, really nice language, Cello, which is a high-level C library, and TensorFlow. So another lesson from the trench is I was in a project to compute the solar irradiance of basically how to put PV panels on top of rooftops to maximize the electricity generation. So this is a hard problem because it takes as an input a 3D scan of your city, plus the position, you have to compute the position of the sun at any point in time. So every hour, if you are in January, the sun is going to be lower on the horizon. If you are in the summer, you're going to be higher in the horizon, and so on and so forth. And you have to compute direct rays, indirect rays, and scattered rays. This is a computation that used to take 3 weeks on a big IBM machine with 50 cores, which was state-of-the-art in 2014, and a lot of RAM and so on. 3 weeks to run that computation. That with using that framework. That framework is coded in C. You cannot say it's interpreted and so on. No. This thing is coded in C. So okay. So I said I can do better. So and I did. So I recoded it. So I took the problem. I followed the rule that I showed you. I coded it in TensorFlow. So not only I coded it in such a way to scale, but I changed also the model of computation behind the scene. I went from an imperative, strict model of computation to a data flow-based computation. And because it's parallel friendly, it enabled me to scale. So I went from 3 weeks to 3 hours. This was on a desktop machine. 3 weeks to 3 hours on a desktop machine on CPU. Then when I did the implementation on GPU, I went from 3 hours to 20 minutes. This changed the life of the researcher. I said, look, now you can do multiple iteration. And actually, they improved the model to take PV panels on facade, because now you can put transparent photovoltaic panels on window. And you compute basically how much you can generate. Okay? This is using that a variant of that software. Okay? So, and we did a paper together. So here, the message is choose your model wisely. Okay? Because you have models of computation which are more parallel friendly than others. Okay? So for instance, the actor model, so we're going to go back to the original subject at hand, Apache Spark, big data stuff and so on. They have a model of computation. They implement a model of computation. And Spark in particular, they used the akka framework. Akka is the actor, is an implementation of the actor framework. It was pioneered by Carl Hewitt in the 70s, 80s. To basically have a model of computation which is more parallel friendly than the regular one, and to avoid the von Neumann bottleneck, basically. Same for interaction nets, which was proposed by a researcher in France, Mr. Lafont, in '97, which is starting to be more popular again. Kahn process network from Gilles Kahn, who I had the chance to meet before he passed away in 2006. A model of computation which is also parallel friendly. And so on and so forth. So that TensorFlow is a data flow. It's not a synchronous data flow, but a synchronous data flow model of computation. Okay. So another lesson from the trench, and that paper scared a lot of people in my field, in the distributed computing field. That paper was wrote by Frank Macheri and people that were back then at Microsoft Research, top-notch researchers, Then after they scrapped my MSR in Silicon Valley, so those guys went without a job, and including some Turing Award people actually. And they wrote a paper because we had a wave of Apache Spark, Praeger, Kafka, and so on, and they wanted to make sense of all of those. And what he did is he took a graph and he computed the page rank on it, and so he compared it with Apache Spark, Apache Giraffe, GraphLab, GraphX, and so on. And he realized that his laptop was, he implemented a system called Naiad, which is timely data flow, again, a different model of computation. And he implemented in Rust. And it went super fast. So it was basically chunking big, large data set that would fit on a laptop, because you still, you have a decent laptop these days, but you would go very, very fast, actually. And this, when I read that paper, I was anxious, because are we using the wrong tools for doing the jobs that we're planning to do? So am I abusing Apache Spark? I could do something way faster. But that I knew, because Apache Spark, when it was created by the Berkeley people, it was never for performance. It was to solve the issue that Apache Hadoop had. And I will talk to you about that after, if I have time. But it was to solve Apache Hadoop issue, okay? So I'm going to go fast on that one. This was just to say that in HPC, those three languages are still king. So that gentleman on the left is John Bacchus, who is the inventor of Fortran, by the way, who won a Turing Award for that. And he was the first proponent of functional level programming, what is functional languages, basically. And I put a bunch that so I'm a sucker for programming languages. So I did some tests with Chapel. Chapel is back then it was Cray, now it was bought by HPE. And they have a nice parallel-friendly programming language called Chapel. Julia from MIT. We have Rust, Tai Chi Lang from MIT as well. The C with the Lambda is called SAC for Single Assignment C. Very nice. It's an array programming language. Mojo for modular. Doing AI is great. And also the Intel One API. So just for your information. So also I'll try to go quick, because otherwise I won't have time to go on MeluXina and do some big data stuff. So we are running top-notch job on MeluXina, including this project, which is a flagship project of the European Commission called Destiny. Destiny is from ECMWF, EUMETSAT, and ESA to basically create a digital twin of the Earth to understand the climate change. Okay, and those guys, ECMWF stands for European Center for Medium Range Weather Forecast. I had the chance to visit them in Bologna. They have big HPCs. And so they have a lot of, so they do weather forecasts for whole Europe. So their clients are Météo France, IRM in Belgium, and these kind of things. And they compute for civilian and military as well. And that's why they have two HPCs, to make sure that if one goes down, the other one. And they're also involved in this research project to leverage the history that spanned 35 years of weather model. I visited the room where they have the tape archive. They have, back then it was 750 petabytes worth of data on tape. It was huge. It was as huge as this room, basically. And the goal is to reuse the data that were collected in the past, so the prediction plus the results, and replay it to validate their model, so they can have a predictable tool to predict the future, okay? Those guys were supposed to run only on the pre-exascale machine, because they run, and brace yourself, in one day, their simulation run generates 1 petabyte of data in a single day. So first of all, we say, guys, you cannot come on MeluXina because you're going to fill up the storage in 20 days. No, but they came on MeluXina to start developing. And they liked it so much, actually, because they were never meant to run on MeluXina, because we were the second one online, actually, from the EuroHPC machines. They liked it so much that they've asked EuroHPC for an amendment to run on MeluXina. Okay, so they are doing development on MeluXina. Our friends from SES, they did a nice simulation to minimize the number of satellites they would put in orbit while maintaining full coverage of the whole planet. And they realized that with 11 satellites, they could do as good as 20. So it's a pure optimization problem. Okay, where you place your satellites in space, in different orbits and so on. They went from 20 satellites to 11. So 9 satellites saved. And I don't know the cost of the satellite, but it's pretty sure this can equate to millions or hundreds of millions of savings. So not bad, I would say. Okay. Flooding model, important, especially after 2021, where we were shocked in Luxembourg and in Germany and so on. RSS Hydro, a nice startup company, they have a nice model where they can compute flooding maps. And they came on MeluXina and they went from CPU to GPU and we helped them pour the code. Well, they have a brilliant engineer, but we supported them and they went 10x, okay? So they can go 10 times faster. We also support Center of Excellence, which are EuroHPC funded project. So from space, from the space world, from material science, a biological one, Ginkgo, or Ginkgo for the so it's a nice library for mixed precision linear algebra from Hartwig Hans, actually is running also on MeluXina. We have a collaboration with iCheck, so our peer in Ireland. So we are not only we are also running 2 countries worth of project. So we're running not only Luxembourg but also Ireland because they are in between machines. So they are actually setting up their new machine, but it's not there yet. But we had an agreement with them, so we basically. Replied to a tender, we won the tender and we are supporting them. We have 800 of their researchers from all the universities across Ireland running on MeluXina. Very nice collaboration, and we also do trainings together. We have projects directly from the European Commission. So that goes without saying, I didn't specify, but all those projects have large data behind the scene. Huh? They don't come on MeluXina with 10 megabytes. Huh? So same for this one. They came with a lot of data from the European Commission. So it's the e-translation service team that is in charge of translating all the documents from the EU in all the languages of the EU, all the official documents. And they train their model on MeluXina, okay? And we help them to optimize their model. So they really loved it. Actually, they want to come back because I received a message yesterday saying that we would like to proceed with a second round. That I cannot disclose who it is, but it's a compliance. They are into compliance. They use AI and LLM and RAGs and so on, so to increase the productivity. So yeah, they also used MeluXina to train on-premise their LLM. Okay, you can do that, without going to the cloud and lose the data and so on, because the data remains in Luxembourg. Okay, same for a bank, but it's not really basically the same. We have a specific agreement, partnership. Here you see our CEO, Arnaud Lambert, with his equivalent of JAXA, and the ministers, Lex Deles and the Crown Prince. We signed an agreement with the Japanese Aerospace Agency. So they came last year and they were interested in quantum computing. And so we gave them a training, a dedicated custom training. So with people that were physically there and people in Japan. So we had to go at 7 a.m. So to make sure that those guys can attend. So give them a training and so on because they were interested. They have access to our system. We're supposed to have access to the system as well. So they are running mostly CFD simulation for rockets, for combustion engine and so on. So they have the A64FX CPU, great CPU. I think I consider it the best CPU in the world. It's only my opinion. But so yeah, we have an agreement with them as well. So and this one is the last one. Then after we'll go faster. I have 21 minutes. I'll try to go faster. But this one is dear to my heart. Why? Because we are reviewing the project that come on EuroHPC share of the machine. And sometimes, we have sometimes big projects. So when we read the project, the name ring the bell. I was like, so it was him. So for those of you who don't know, I won't spoil it now. So it was Giorgio Parisi. I said, I know that name. I know that name from somewhere, but I didn't know where. Then when if you Google him, that guy won a Nobel Prize in physics in 2021 for his work in complexity theory in physics and so on. And he applied to MeluXina. So when you apply to the EuroHPC, you can choose, or you can put all the machines because you don't care about the machines where you run. But he only put MeluXina. He said, no, I want to run on MeluXina because I like the stability of the machine. Because he came before, I didn't know that, he came before with a small benchmark project, but he liked the stability and the support. Then he came back with his bigger project, and he ran. And it was in 2022. Him and his team were the best user you can possibly get. He came in April 2022, He said, after 3 days he started his project, I've run out of my allocation because we give allocation per month to make sure that everyone has a fair share. So after 3 days, I've exhausted my allocation. Can you give me my N+1 month? Say, sure. Here is your, I don't know, it was 10,000 hours per month. Okay, after 3 days, again, we have exhausted our allocation. Can you give us, okay, I see where it's going. So what he did in the span of 3 months, he computed what is the equivalent of 1 year of computation in 3 months. Because in 2022, we had more availability. Okay, so he computed everything that was supposed to do in 1 year in 3 months. So he finished in July, and then after, never heard of boo or ba. He said, thanks, great support, see you, goodbye. Okay. And then 2 years after, he publishes in Nature this paper based on this simulation, where he's thanking us. Thank you for your expertise and so on. And actually, he published 2 papers, one in Nature and the other one in Computational Physics Letter, that potentially could gain, this could have gained him another Nobel Prize, by the way. But, one is enough. So we're also involved heavily in European projects. One is called Deploy AI, where we're supposed to give a platform for the SMEs in Europe to build, train, and deploy AI. It's very nice. It's still in progress, but we're going to do some announcements soon that will resonate throughout Europe. Big project, 28 partners, 28 million euros funding. Big project, bit chaotic in terms of coordination because you have that many members, but it's really very impressive one. Another one that we are really proud of participating to is called Epicure, and there we give advanced support. When I say advanced support to the researchers, really advanced. Code porting, performance optimization, and so on. So this is the kickoff in Portugal. Here, it's in the context of that project, we also give trainings and workshop, and this was done by my colleagues Emmanuel Kiefer around the FPGA on MeluXina. And the first project that we supported was with Institut Super. So for people that come from France or Europe, that institute is very well known for its aerodynamics and so on. So and they have a proprietary code called IC3, and they basically solved Navier-Stokes equation that I showed you before for next generation air intake for jet fighters. So for supersonic air intake. And so it means that the flow of air arrive at supersonic speed. And they have a big simulation, a lot of code, 300,000 lines of code. And this is actually a reality of a real code, of a real scientific code. You have a mix of everything. So here you have C++, C, Python, Fortran, modern Fortran, not Fortran legacy. So when you approach such a code, you have to approach it diligently, okay? And we ran profilers, and the goal of that project was to vectorize the code intranode. So we helped him. Okay, we showed that we can increase the arithmetic usage of the CPU and so forth. This is the kind of code, by the way, that you can see in scientific code. You see those dash, the underscore M256, those are called SIMD intrinsics. This is what we see when we open the source code. That can be scary. Okay, so but this is life. So we try also to use modern tools such as Coccinelle. So Coccinelle is a nice tool from INRIA, from Jules Lawal and his partner. Unfortunately, also he died a couple of years ago. Gilles Muller, great researcher from INRIA. They came up with a tool to patch the Linux kernel, but in a correct way. And they came up with a language called SMPL for Semantic Patch Language, to modernize basically the code of the Linux kernel. And at some point, I think she went into the Hall of Fame of Linux contributor because she was using that tool to automate all of this. So basically here, you create what is called a nest patch. And here you basically put the patterns. You say, the plus is, I want to add this when you see this. And this is an identifier. And when you see the F, replace that function with an equivalent with the F and the less than. And this is basically to codify a code, a C code, okay? And this is what basically, it creates you a patch, and then you apply the patch, and then you run the code and to see if it's working or not. It's very neat. It's only working, unfortunately, for C and C++. They are working on Rust, but it's very, very neat if you want to do code modification with certain guarantees. Because when you modify code, we never know if we're going to introduce a bug. because we're not expert in the domain. So generally what we ask is test cases. That's why they're important, because we are, again, when we ran IC3, we didn't know if the output was correct or not. So we had to have some kind of a level of insurance. Same here, a code that we supported in the last weeks called SHISM. So SHISM is a big scientific code for modeling oceans, ocean current and so on. Very important to understand our climate, obviously. That code is huge. 1.7 million line of code. Fortran, modern Fortran, and here you have a funny one, Fortran legacy. So, because, you know, it's full of everything in there. So, but this is the reality of a scientific code. Everything is in there. And you have to make sense of all of this. And they had an issue with MPI, and we solved it. So we managed to see it was due to communication issue that they're having. So in their software, they have different, basically, steps, force preparation, the solver, and so on. So we basically solved it. So what's next for MeluXina? And then I'm completely out of time, sorry. So we are working on MeluXina Q, already told that up front. So we're going to go for in silico spin qubit technology. So quantum processor using silicon as a substrate. We're going to go for 10 qubit first, and then after we're going to do a midlife upgrade at 80 qubits. Okay? And so we expect it next year, but we'll see. And we're going to integrate with current MeluXina. And then we are actually doing some awareness session. We did a big full day training on quantum computing last year with 50 people, and it was really nice. Then MeluXina AI, obviously, it's taking a lot of time these days. This is an historic picture where the Luxembourgish mafia is, including myself. So all the 13 AI factories over there, because this was the first AI factory, then after they had a second round, third round, and so on. So we did a nice picture in Poland for the EuroHPC summit. Obviously, we made the news, and so on. So now, big data, I have 13 minutes, great. So motivation, I will spare you the big 5V and so on. I think you know that well. So, okay, data science on MeluXina has a different meaning, obviously, because we have petabytes rather than megabytes and gigabytes. So this is what we target. Terabytes and petabytes, okay? We don't go under. So what we have, and actually let me show you, we have Jupyter Lab instance. So with Open on Demand, you can spawn on the fly. So I already spawned one, but let me show you how you spawn it here. So Jupyter Notebook, you can choose the number of nodes. If I want to put 100, I put 100. It will not go through because of the QoS, but okay. The accounting, because we need to make sure that you pay it at the end of the day. I mean, it's not a credit card, it's just the account in Slurm, okay? So here I'm part of LXP, so I put LXP. The QoS, default, dev, long, urgent, and so on, and short. And here the time limit, and then the partition on which you want to run. If I want to run CPU, GPU, large memory, FPGA, and then you click launch. Okay, and this basically will launch, I already did, my interactive session. So it's already launched, I'm gonna connect to it, and it's gonna launch a Jupyter Lab for me on MeluXina, on MEL2177, a GPU node. And I have a bunch of kernels that are there. Okay, it's nothing. So it's connecting to the one that I already created, so for Dask. So Dask is an equivalent of Apache Spark. So while it's running, I'm gonna go a bit fast on Spark. So Spark was born in Berkeley, in the AMP lab by those two guys. I mean, there are more than that, but Matej and Hayan Stoica. And this paper came out basically introducing Spark to the world from NSDI. So Usenix conferences is where you will see the next generation frameworks that will come out from research to the world. So if you want to get to be at state of the art, you read the proceedings every year, like I did. They're for free, actually, you can read them. So when I read them, because those guys were in my domain field, so I read them, I was like, wow, this is great. Because the good thing is that they open source the code from really early on. So I start using Spark version 0.2 or something like this. So Spark introduced the concept of resilient distributed data sets, which is distributed data set, but improving on, basically, by the way, those guys, they also created this company and are now billionaires, by the way. They were basically solving the issue that MapReduce had. And the MapReduce had as an issue that, so first of all, MapReduce was from Google, and the open source implementation of MapReduce and Google File System were Hadoop MapReduce and Hadoop HDFS. And basically here you have your mapper, you're splitting your initial text into lines, and each line, you're gonna map it with an integer each time that you see basically a token. And then you shuffle to basically group them together, and then you reduce to sum up the occurrences. And then after the end, after reduce phase, you have the final result. I've seen bear 2 times, I've seen car 3 times, I've seen deer, and so on, okay? This is MapReduce. So I guess you know it. So HDFS, this is the architecture. I will not go through it, but HDFS is a distributed architecture where you have the name nodes, basically the location of the data nodes that actually hold the data. So you first, you as a client, you query the name node, then you get the data node to respond to you, okay? And it uses socket for communication. And the issue when you're doing a MapReduce computation using HDFS in the back is that between iteration, you're reading on the disk, from the disk, and it's super slow. And the intuition from those guys was, can we use in-memory computing to actually speed that up? And they did. And they went 10x faster. So Apache Spark has a nice architecture, and you have to understand that to actually make sense of Apache Spark. You have the driver that drives the computation. You have the worker node, and behind the scene you have HDFS. And Zookeeper, it's a coordination system. So it supports iterative algorithm, which MapReduce was not good at, okay? And also, the good thing about Apache Spark is it's lineage behind the scenes. So it means that it's keeping track of the transformation that you're actually doing on the graph, and to make sure that if one node fails, you can recompute only that part. In MapReduce case, it was not the case. If one node fails, you had to redo the computation over again. So you would lose a lot of time. So that's where it was born. And by the way, here was a state-of-the-art software stack for doing distributed computing when I was at LIST. I put that between 2013 and 2015. And I did that on Apache Mesos, which is not used anymore, but it was a very nice piece of technology. And all those I put for my colleagues to use. And I'm talking about a decade ago. Okay, so this was state-of-the-art. So I have a long history with Apache Spark, actually. So again, just to go faster on this one. So Apache Spark, when it came out, they stick to the JVM world because the big data world was mostly on Java, JVM. So they could have gone for better performance if they would have implemented in C and C++, but they say, no, we want to be friendly to our other frameworks. So we want to stick to the JVM, okay. So, but they wanted to be modern. And they said, yeah, there is this new language called Scala, which has some functional feature and that you can use. So it's more modern, still based on on top of the JVM, but more modern. So the first implementation of Spark was on Scala, okay? So you have immutability, I mean, other implementation of immutability. And Spark offers you 2 types of action, 2 types of operation that you can do on those RDDs, the transformation and the actions. The transformation are lazily evaluated. It means that when you do a map and a filter, it doesn't return you the result until you do an action, until you say, okay, I want to map, I take this value, I multiply it by 2, and I take this text, I'm gonna split it by line, I'm gonna basically filter the error because I'm interested in all the errors and so on. But it's not gonna give you basically the result right away until you do an action. And the action is count me how many times you do X and so on, okay? So this is basically what you can see here. I ran it a couple of days ago, just for you as a reference. So I created a list of 1 million or 10 million numbers. I created an RDD out of it, of int, so using the Spark context parallelize. And then after, I put them in cache, because the good thing about Apache Spark is the controllability. You can say, I want this data to be in cache, in memory, and you can put that. Or I want to repartition the data on the fly. It's very neat. And yes, and then I want to count the number of numbers, and I want to reduce it. So it means that I'm going to basically do 1 plus 2 on 1, 3 plus 4, and I'm going to sum it in parallel. Okay, but yeah, not very interesting operation. But this is basically the concept of lineage. It's going to track the graph of operation to make sure that if something goes wrong, it can relaunch it. So I started to get interested in Spark again after a decade of ignorance. Yeah. Yeah, it's okay? Ah, sorry. So from Spark 2.x to 3.x, they came with GPU support. So now it's way better to use Spark on GPU. It was a bit of a nightmare before. You could, it was harder, but now it supports basically new workloads and so on. And if you basically complement this with Rapids, then you can do really nice things. So Rapids come with, for instance, QDF, which is a CUDA data frame. And you can actually use it in the context of Spark as well. So they created a jar, actually, where you can basically reuse those nice libraries from Rapids. Okay, so I'm going to fast on this one. So it's leveraging also UCX, which is a communication library that leverages the InfiniBand, okay? And use Apache Arrow in the back, okay? So Apache Arrow is a standardized way to load data in memory, okay? And they use a specific shuffler, but I'll not go into the details. I'm going to share those slides anyway. So then I'm going to briefly talk about Dask, and then I will conclude because I have 3 minutes and 58 seconds. So Dask is an equivalent of Spark, but in Python, in the Python world. It's very neat, but it uses different mechanisms. So it doesn't use akka actors behind the scene. It uses coroutines and future, which is another way of doing parallel computing. And it's also based on UCX as well, so they can leverage the InfiniBand interconnect to go fast. And what we have, and I'm gonna, because I won't have time to show you, unfortunately, but I had here a notebook. So if you want, I mean, here, Rapids. Emmanuel did a very nice notebook, which is, you can find it on our own GitHub, to do Dask and Rapids. And I mean, if you have access to MeluXina, but for those of you who have the chance to have access, for those of you who do not, you can come to see us, where you can basically launch Rapids on Jupyter Lab, and basically take advantage of all the GPUs and so on. And if you just follow through, it will run, and it's incredibly well done. So just take the reference for you, but yes. So here I go for all the Dask architecture. It's different, but okay, it's a really high-level view. It's like Spark, but different mechanism behind the scene. And they went for NumPy compatibility from the get-go, which is not the case for Spark because, well, NumPy did not exist back then. So here it's more modern. Dask is really, really nice, a nice project, and it integrates very well with Rapids. So it's very, very neat. So you have dashboard and so on. So this is one that we used for doing the training because we did the training at Synergy, which was the a new event that we put in place for supercomputing and quantum. So my colleague did a fantastic job in showing that. So yeah, other tools worth a try. You can also have a look. Root from CERN. So the Higgs boson was discovered using that tool. So they generate also petabytes worth of data, and they use Root as for doing data science. Arcuda from HPE using Cray Chapel, they have a NumPy interface, very nice. And then you have other frameworks such as Exo to basically go from high-level Python down to really generate C code, which is super efficient. It's from MIT, it's really nice. And Spiral from Carnegie Mellon also to go from high-level formal operation for FFT, so fast Fourier transform, down to C code and CUDA codes. Very nice. And last but not least, languages which are out of this world. So I used to, as I said, I'm a language sucker, and I started to have an interest back into array programming languages, such as APL, which stands for Hey Programming Language, from Kenneth Arverson, who won the Turing Award for that. And there is Dialog APL, J, which is an open source equivalent. It's the last project where he worked on. And I start to have to explore those in the context of HPC, and they are incredibly powerful languages. But you need to think differently when you use those. But those tools are actually KX is used in the finance world. So all the finance guys at Wall Street and so on, the data processing, a lot of them using KX. It's incredibly powerful. So I urge you to go and have a look at those. And finally, I will finish with that. We are still the best processor in the world. And it's not me saying it, it's scientists. We have the capacity to go from petaflops to even more, and we only consume 20 to 25 watts, so we're very efficient. And we have still the creativity advantage over a machine, okay? It doesn't mean that what is getting out there, the AI craziness that's happening, is not helpful. It is, but we're still the best, because a GPU, trust me, they use a lot of power, and we don't, but we are still very smart, actually. So yes, so as I said, we're not machine. This is reference in movies, the Hidden Figures, Imitation Game, Mars, and Jurassic Park, where you have a connection machine in the back, which is from Thinking Systems, and very good books. They are mostly on quantum, because that's where I focus on these days. But you have, actually, and I can say it proudly, I bought a book from one of my users, so the Nobel Prize winner, he wrote a book, and beautiful book on his whole history. Nice book about, I love music, I'm a guitar player, and I love mathematics, so I said, was there a guy that did actually a book on a mathematical approach to learn music? And yes, of course. And I bought those two books, incredible books, and a great book from Dick Hamming, basically learning how to learn, okay? So the art of doing science engineering. This is probably one of the greatest books that you could ever read, okay? And that's it. So I went 1 minute over time, so it's fine.